Hope everyone was able to get another coffee or whatever into them. We're ready to go for this afternoon. So I'm very excited to introduce Heidi Jandrus. Actually, probably coming to us. I would say the furthest, but I think Calgary is still a little bit further away from Toronto. So, but Heidi is stateside with us this afternoon. So Heidi grew up immersed in all things concrete block and worked as a welder in the plant before getting her Bachelor of Architecture at the Pratt Institute in Brooklyn, New York. She is a current candidate for Master's Sustainable Building Systems degree at Northeastern University. She is part of the third generation of her family business, Jandrus Block in New England, and provides technical services while researching ways to improve the efficiency and sustainability of their manufacturing process. So we certainly appreciate your time this afternoon, and really excited for your presentation. I think we laid a lot of good groundwork for what you're about to talk about this morning.
Yeah, hi Andrew. Thanks for asking me to join. I'm just going to share my screen. All right, you got it?
Yep.
All right. So yeah, Andrew gave me a pretty comprehensive introduction. My name is Heidi Jandrus with Jandrus Block. We are located in New England, and I'm going to talk today about operational carbon, embodied carbon, and then also a kind of new area of research that I've been working quite a bit with carbon sequestration with concrete masonry. So first, I'm going to go over a bit of an agenda so you know what you're in for. I'm going to talk about kind of definitions of operational and embodied carbon and how that relates to concrete, and in particular dry cast concrete, and also briefly what this means for greenhouse gases and how they work. So I am going to talk about the geologic carbon cycle. And the reason for this is that I put this presentation based on what I present to architects in my area and what I find to be very successful and what I get good response from. And so this presentation is a bit of kind of what definitions of kind of terms that we've seen a lot in the industry lately, and then also, just kind of to show you what I present on the topics. Like I said, because I've been getting very good feedback from them. So I find it helpful to talk about the role that carbon plays in the big picture of the Earth's natural cycles. It helps to make sense of the concept of carbon sequestration, which we're going to get to the portion later in the presentation. So we're going to look at some climate change scenarios and some steps towards the solution. I find it very effective to talk about some of these scenarios that scientists are currently talking about. It helps to set the framework of how important this work is and how seriously we're taking it, as a concrete producer. And then I talk about carbon sequestration, what it is and why it happens with concrete, and in particular concrete masonry, which is dry cast concrete. And I'm going to talk about why that is important when we're talking about sequestration. I've attempted to take an extremely complex subject and present it in a simplified and understandable way without glossing anything over. So it's a pretty big ask, and you can let me know how successful I am at it when I'm done. So I'm going to do a really quick update on what NCMA is doing with carbon sequestration testing. I have a couple of slides that were presented at mid-year in Milwaukee this past summer, and it explains where NCMA is with developing testing protocol for dry cast products. And then I'm gonna just show a couple of slides on a simple LCA that I did as one of the projects. Andrew mentioned that I'm currently a candidate for my master's degree at the College of Engineering for Sustainable Building Systems. So this is a class that I took, and it was my project. So in what it does, I compare different structural systems and kind of shows what the embodied carbon is for each one of these systems. And I think it can be a really great jumping off point for where we're going with this sequestration and kind of the rates that we're seeing. It can be a kind of baseline, you know, and how we can kind of lower our embodied carbon and show how we actually can lower our embodied carbon. So a little bit about who we are. Jandris Block, we're located in central Massachusetts. We manufacture block only. We do not do pavers or anything else. We're just strictly block and retaining walls. A little bit about who I am. Andrew said, I mentioned I'm third generation. I kind of grew up as daddy's little helper. He used to tell me that the little trowels were meant for kids. So that was my main tool growing up. I worked as a welder at the plant for a lot of years. I then went to get my bachelor's degree in architecture at Pratt Institute in New York. And I've already mentioned I'm currently enrolled in my master's at Northeastern. So just a little bit about what we do. I mean, we do gray block, it's structural, it's durable, it's very resilient, it's got good thermal mass. We do a lot of firewalls with this. We also do architectural CMU, which has all of those attributes, plus it's very beautiful. We do both structural and veneers with architectural block. We use a lot of specialized aggregates. We have multiple colors and finishes, such as we do a smooth integrally colored unit. We do split face and ground face. We do half high ground face. Here we have one of our polished units, which doesn't have any kind of extra coatings on it. It's just all about the finishing process. And similar to that, we have a textured polished, which is a similar process, but it's got a bit of a kind of leathery texture to it. And we also do segmental retaining walls. So I'm gonna talk now about embodied carbon versus operational carbon. This is a slide from the Carbon Leadership Forum's website. And they've recently changed the embodied carbon to have this kind of upfront embodied carbon, which is kind of promising. And it kind of ties into something else that I'm going to bring up in this presentation about, you know, there's one thing to have your upfront embodied carbon, but then what about durable products like ours that last, right? So that comes into LCA, and, you know, the less you replace them, the less embodied carbon is going to be involved. So first, I mean, operational carbon, this is the one that's been around for quite a while. This is what all of, you know, the building energy consumption is about. Concrete masonry in particular, and the thermal mass can really kind of help with operational carbon if designers know how to use it. So here we have a chart, and I'm sure many of you have seen this chart before. It shows sort of how thermal mass works. And in green, we have the interior temperature of a space with a, you know, that's a mass wall structure. In red, we have the interior temperature of a light frame structure. And then in blue, we have the exterior temperature. So what this chart shows is how, you know, when you have a light frame structure, the internal temperature just follows whatever's going on the outside, where when we have mass walls, I mean, this is what we call thermal lag, where it actually can kind of hold in the conditioned space. And I know that we think a lot of mass walls, you know, in the Southwest of the United States, you know, because there's a lot of structures out there, but I mean, it can work also in northern climates as well. I mean, I'm in New England, you know, so here we can actually use the mass on the inside of the insulation to hold in the conditioned space. Just kind of a real world sort of how we can feel thermal mass, really. This is Marsha's garage. Marsha's my sister. And in case you hadn't caught on, this is a family business, and her garage is made out of block. And I took this photo a couple of years ago when we used to still have parties. And it was one of those days in August, and it was like, 105, 100 degrees. I'm exaggerating if I say 105, but it felt 100 degrees. And as soon as you walk into this garage, it's immediately felt about 15 degrees cooler. And that's because of all of that thermal mass working for us. And if you can imagine, I grew up in a almost 100% block house, right? So we had block walls, block floors, block stairs. There was wood beams. There was actually a block checkerboard in the block floor. which was in front of the block fireplace. So if you get my drift, there was a lot of block. But we never needed air conditioning in the summertime. And my father would make sure that we kept the windows closed during the day and open them at night to get that kind of, that flush coming through. But it's, so I grew up knowing firsthand kind of the benefits of thermal mass. And I think as an industry, we really need to, kind of drive this point home to designers. So looking at the 2030 palette, they've got a couple of strategies in here that use thermal mass, and one is a heat storage wall. So it's meant to take solar radiation and then release it back into the space at night. Another version of this, which is similar but a little bit different, is a thermal storage wall, where the glazing is on the exterior, the wall is not too far in, and it's meant to take in the heat and then release it into the adjacent space at night, through the other side of the wall. So feelings and feeling warmth and cool is one thing, but ASHRAE actually takes into account the benefits of thermal mass. So this is a chart out of ASHRAE 90.1 and looking at climate zone 5, which is where Massachusetts is. And ASHRAE takes into account benefits of thermal mass. So the mass wall U factor required is a 0.09, where a metal framed, for example, is a 0.064. So this is one of the ways that we can kind of look at code-based values for thermal mass. And kind of taking this a bit, backtracking this a little bit, I'm looking at two different assemblies here, and one assembly is a metal stud with 2 inches of insulation versus a block backup with 2 inches of insulation. So we're looking at different structural systems with the exact same amount of insulation. And again, in climate zone 5, this assembly will fail that code by 14% with 2 inches of insulation, where if we look at a block backup, this with the same amount of insulation exceeds the code by 36%. So this is kind of a real world way and code-based way to kind of to see how thermal mass works. So that is how operational and how mass walls can kind of fit into energy use. And before I move on to embodied carbon, I'd like to take a little detour to a carbon category that I think our industry really needs to bring into the world of carbon accounting. So I mentioned earlier, we've got the upfront embodied carbon, which I'm going to go into. But what about longevity of materials over time, right? Like the more durable the materials are, the less replacements needed, the less embodied carbon over time. I just kind of threw out a couple ideas for what could we call this, and maybe it already has a name. But I mean, could it be called durable embodied carbon? Length of service embodied carbon, long term, like any of these things, right? And we kind of earlier in the morning we touched on these kind of topics, and this is really where Masonry can really make a difference in the world of carbon. And just like this is one of those Sears homes back over 100 years ago now. Kind of my family business got started with one of these little handmade machines here, and Sears used to sell these as a kit, right? If you start looking at, I know in the U.S. where I am in the Northeast, once you start seeing these little houses, you start seeing them everywhere. Like they were made out of block. There's some that are made out of wood. But these were built over 100 years ago. And I mean, if you see them today, I mean, they still look great, right? And this is before, any of the kind of, admixtures. I mean, this is just kind of really speaks to the longevity of concrete. And something else, I went to a seminar that was primarily about perceptions, and how, like, can you really trust the things that you perceive? And one of them was, and myself included, like everybody thinks that medieval castles are made out of masonry, right? Like we see them everywhere. They're in the movies, right? So that's what we think, or that's what I think anyway. And it's really not reality. Most of them are actually wood. They just aren't around anymore. So I mean, that really, really speaks to the longevity of masonry. So back to the agenda. Upfront embodied carbon, right? So embodied carbon is how much carbon is used by kind of like all of the upstream, right? So at my manufacturing plant, right, like we did our environmental product declarations, and we included in our environmental product declarations, all of the upstream is included, right? So here's a look at one of our normal weight EPDs, right? And we're showing here global warming potential, and it is reported in equivalent CO2, right? So equivalent CO2, carbon dioxide equivalents. So the difference between global warming potential on EPDs and embodied carbon is that embodied carbon is carbon. Global warming potential includes all of the other greenhouse gases that contribute to climate change, right? So for example, methane is one of them, right? So methane is approximately 27% more potent a greenhouse gas than carbon dioxide. So any methane that was given off in the manufacture of our block would have been converted to carbon dioxide equivalents, and it gets reported in the global warming potential. So they're sort of the same thing, but not exactly. So I just wanted to make a clarification there. And very quickly, kind of what global warming potential is and how greenhouse gases work. So greenhouse gases, I mean, literally they work like a greenhouse, right? So all these gases in the atmosphere, they allow the solar radiation to come through them. But then once that solar radiation gets converted to heat, it's not allowed out. So all of these greenhouse gases in the atmosphere work the same way that a greenhouse does, and it allows radiation in, but does not let it out, which is why we're seeing warming climates. So I'm going to go now into the carbon cycle. The largest reservoir of carbon in gigatons on Earth lies in its sediments, and this number includes fossil fuels and rocks, including limestone, which is very, very important for cement production. And over the intervals of millions of years, slow exchanges among rock and surface reservoirs cause large changes in atmospheric CO2, right? So it comes out, it goes back in. So without human intervention, CO2 primarily enters the Earth's atmosphere from deep within its interior through the release of gases in volcanoes and hot springs, such as Yellowstone National Park in Wyoming. So this is one of the ways that CO2 gets into the environment naturally. And one of the ways that it gets out is through chemical weathering. So chemical weathering removes CO2 from the atmosphere by combining with rainwater to make carbonic acid. And this will slowly attack silica minerals, such as quartz and feldspar. Part of this weathered rock is chemically converted to clay, and then it's stored in the soil below ground. It also produces several types of dissolved ions, and these ions are carried by rivers into the ocean. So from there, ocean plankton uses these ions along with carbon dioxide from the atmosphere to make the shells for these little creatures, right? So these shells are also limestone, calcium carbonate. Sound familiar? We're getting into cement production here, and we're going to talk about this later. So as these little animals die, the limestone is then deposited as sediments at the bottom of the ocean. And then over time, as the plates start to cover each other, the cycle continues, so over and over. So this is how the Earth regulates CO2 levels in the atmosphere, is through this very, very long cycle. So it's part of feedback loops that regulate the climate on the Earth, and it's been this way for billions of years. So at the onset of a warming trend, increased temperature and precipitation increases the chemical weathering, which increases CO2 removal, and then the initial warming is reduced. And same vice versa, in a colder climate, temperature and precipitation is decreased, all of the chemical weathering is decreased, and then CO2 removal is decreased. And then it reduces that initial cooling trend. So there is a distinct correlation between atmospheric CO2 and the temperature on Earth. These data points were collected in Antarctica in an ice core. And these data points were initially published in the Nature Research Journal back in 1999. They reconstruct temperature and greenhouse gases in the atmosphere over the last 425,000 years. So in blue, we're seeing carbon dioxide, and in gray, we're seeing the temperature anomalies. So correlations between them, we can see how as CO2 rises, temperature slowly rises. As it falls, the temperature falls. So these peaks and valleys represent the cyclical nature of the interglacial periods, and they're actually caused by this, the Earth's cyclical orbital changes. So while this correlation is well documented, temperature changes and climate variability, I mean, they aren't only caused by CO2. There's several other natural forcings, such as solar activity. We've got volcanic activity, dust in the atmosphere, vapor in the atmosphere also acts as a greenhouse gas, which can also affect global temperatures. But the key word here is natural. So the difference now is that since the Industrial Revolution, us humans have been spewing more CO2 into the environment and at a much quicker rate than any natural forcing. So here we're looking at some of these data points, and since the early 1900s, the CO2 levels have been rising much faster than they did even during the last extreme greenhouse climate, which was called the PETM, which stands for Paleocene Eocene Thermal Maximum. And that was about 55 million years ago, and it lasted for about 100,000 years. And this interval was characterized by the highest global temperatures from the Cenozoic era until present. And another thing to note is that it took thousands of years for the temperatures to rise to their highest point. So we're certainly not anywhere near the levels of atmospheric CO2 that we were during that period, but based on our current trajectory, we're headed there much sooner than 100,000 years. And again, our little friend with all of our greenhouse gases makes a warming climate. So at the beginning of that extreme warming, the Earth was already relatively warm, and the temperatures rose between 5 to 8 degrees globally, and it made the temperatures at the poles 74 degrees Fahrenheit, and the ocean waters were 68. And this extreme warming, scientists don't know the exact reason, but they believe it occurred after a massive release of carbon dioxide, methane, and other greenhouse gases, and the causes are unknown. There are a few hypotheses. It could have been, obviously humans weren't around, driving around cars and taking apart an industrial revolution, right? So we can roll that one out. And one of the hypotheses is that there was a rash of wildfires. Another is that giant streams of cold were exposed to volcanoes. Another still is that the mild warming that was already taken place caused methane to be released from the melting tundra. So whatever the cause, during this period of time, there's fossil evidence of ferns and ginkgos in the Arctic Circle. And also there's also fossil evidence of alligators and crocodiles. So during this time, the globe had warmed more than we had seen. And it shows how extreme the effects of climate change can be. And it allows for some pretty striking comparisons. So I'm going to look now at a couple of climate change projections. And the IPCC, which is the Intergovernmental Panel on Climate Change, has developed a series of scenarios for greenhouse gas emissions. In dark blue, we have actual CO2 emissions, which are documented. And these others are called RCPs, or representative concentration pathways. In pink is very high greenhouse gas emissions, and orange is intermediate mitigation 1, and the cyan is 2, and this green is if we have stringent mitigation starting now. And with no effort to do anything, we're going to end up somewhere in here. So I'm going to take the optimistic route and look at fairly drastic lowering of CO2 emissions. And I'm going to take a look at this scenario, and I'm taking a look at a period of the difference in 2 periods of the year 2000 to 2020 versus the data of in this scenario of 2080 to 2100. So we can see here in this climate model that right around the equator, we see the biggest change in temperature. And the reason for this is because of the polar ice caps melting. And because of the change in albedo with reflection, right? So around the equator, the temperature doesn't change as much because the surface remains the same, but where the ice caps are melting, there no longer is the reflection of the solar radiation, so it actually absorbs it, so it makes the temperature change even higher at the poles. So is this enough to bring the alligators back to the Arctic? Probably not, but we can see where this is headed. So an integrated approach is needed, and this was published in Physics Today back in 2014, and it just shows the need for these 4 different strategies. And so we've got mitigation, which is the reduction of emissions, adaptation, which is where resiliency comes in, which is big for our industry, knowledge-based expansion, so scientific development, and also geoengineering. And I'm going to talk a little bit about geoengineering, not because I think it's that important, but I think it's interesting to talk about. So there's several of these sort of strategies out there or ideas out there. And what we need, though, is solutions that don't negatively affect Earth systems as a whole. And they need to work economically and ecologically, right? So this one of Space Mirror is like, I don't know. Seems kind of Star Trek-y and expensive. And it has questionable efficacy, right? So the purpose of this would be to reflect the solar radiation back up. You know, another one is to add iron fertilization to encourage marine life to inhabit the current dead zones. There's likely unintended consequences for this kind of strategy. Another would be putting you know, what's called cloud seeding into the environment, into the atmosphere over the oceans. And that would be, again, to reflect the solar radiation. But I mean, that's very likely to change, you know, global weather patterns. So it sounds very scary, in my humble opinion. But the 2 that seem to have some promise would be afforestation and then also carbon dioxide removal. And I'd like to talk about afforestation for a second. And this would be reintroducing forests and leaving them there so that the carbon can be stored in the trees and the soil beneath. As trees are cut down, not only are animal habitats destroyed, the decapitated trees stop taking in CO2. And also a lot of times they release that CO2 that's stored in the surrounding ground. This is a slide from the USDA website, and it shows how different types of trees hold different amounts of carbon in the soil around them. And this is not just the soil, but it's in the wetlands and the peatlands around them in the forest. And right here from the boreal trees, you can see here from this chart that about 95% of the carbon is actually stored in the soil and is not actually in the trees. So I'm going to leave this one there. You can use your imagination on where we could go with this or where I could go with this. But I'm going to move on to carbon capture. So CO2 is actually taken out of the atmosphere and it's combined with hydrogen to make a fuel which is chemically identical to gasoline. As far as I know, it's very, very costly, but the Wall Street Journal reported on February 12th in 2020 that Exxon, Mobil, Chevron, and Microsoft were actually involved in reducing cost of this carbon capture. So hopefully there's some promise here if we can get the cost down with this. So now we're going into carbon sequestration. And I'm going to go briefly into the chemistry of the concrete and why it happens. But first, I just wanted to show a couple of slides to kind of put it in perspective. And I think we've already seen slides earlier today that show similar things. But this is from Architecture 2030, where building materials and construction is about 11% of CO2 emissions, which is quite a bit. And this is from a paper that the PCA put out within the last year or so that states that cement production is roughly 3% of US CO2 emissions. So there's quite a bit we can do as concrete producers there, and also cement industry. But first, I'm going to talk about how cement production releases CO2. So, because it kind of helps, I think it helps with the understanding of why concrete production is CO2 intensive and then what we can do about it. So CaCO3, aka limestone, little ocean creatures with their shells, is taken out of the quarry. And it's heated up in these big rotary kilns, right? So for scale, we can kind of see these guys here. So these are big, big rotary kilns, and this heat causes a chemical reaction. It's heated up to about 2000 degrees. And for quick and easy numbers, and I really want to stress these are quick and easy numbers, don't hold me to them, but approximately 45% of the CO2 released is due to the energy used to heat this limestone up. So during this, so this heat causes this calcination reaction. CO2, so the CaCO3 is chemically broken apart and CO2 is released, and what we have left is CaOH, which is clinker, right? And it's these little kind of fist-shaped balls. These get ground up to be cement powder. And again, for those quick and easy numbers, approximately 45% of the CO2 release is due to this chemical reaction. So when water and aggregates combine with the cement, it produces concrete. And from the moment the concrete's produced, it begins to reverse this chemical reaction that originally released the CO2. And it begins to sequester CO2 from the atmosphere. So this is chemically combined back permanently into the matrix of the concrete as limestone. And historically, this has been called carbonation. And it's one of the many reasons that concrete shrinks over time. So I'd like to talk now about the similarities between dry cast and wet cast, because this is key for how and why we're doing the current research with concrete masonry. And so some of the similarities, I mean, it's the, raw materials are pretty much the same, just different ratios. If you were to look at, like, these are some curves, like wet cast versus dry cast curves, they look the same. Can't really tell the difference. And I guess here I'll define what dry cast is for those that are not familiar with this term. Dry cast is a zero slump concrete, and it's made on block it's on the machines, which actually I do have some slides on this. So I'm going to move forward. So here on the left, we have our block mixer. Or concrete mixer, and on the right we have wet cast. It's usually, a lot of times mixed in these trucks driving down the street, and it's poured in place. Again, some of the differences. This is our block machine here, and this zero slump concrete comes out, and if I were to go up and grab that, it would crumble in my hands. It's what we call green concrete. Compared to on the right is a slump test, which, one of the kind of performance metrics is how much the concrete will shrink due to water content. So this is one of the big difference between, like dry cast and wet cast. Here is a dry cast concrete block structure, right? It's made by masons compared to a wet cast concrete structure, which is poured in place. So why am I telling you this? Why does this matter? So due to the CMU being dry cast, it has a much more porous structure when compared to wet cast. So on the left here, we have a zoomed in image of a dry cast concrete, and we can kind of see this interconnected void structure. And comparing that on the right with a wet cast with air entrainment, we can see that it's got these, kind of air pockets, but they're completely shut off from each other. So this kind of shows, and because of this, because dry cast has this more porous structure, we have things like absorption requirements for block, in ASTM C90, absorption levels can't be higher than a certain number. And this is also why for exterior applications, we use integral water repellent. So all of our architectural block, we do put the integral water repellent in because of this. So because of this this more porous structure, though, it kind of almost creates like a carbon dioxide sponge. And so one of the ways that we can see this carbonation, which is also called sequestration, is by a phenolphthalein indicator solution test. So where the indicator turns purple, the pH is above 8.6, and where the solution remains colorless, it's below 8.6, which suggests carbonation. So a fully carbonated paste has a pH of about 8.4. So the block on the left is a dry cast and the right is wet cast. So the rate of carbonation in wet cast is slow, approximately 0.4 millimeters per year, and it slows with age. And this image here, this wet cast is somewhere around 6 years old, and the carbonation is shown only at the outer crust of the concrete. And on the left, this one is about 28 days, and you can see that it's kind of going into the middle of the concrete, and it's not just at the surface, and it's happening at a much quicker rate. So until recently, the concrete masonry industry assumed that CMU carbonated the same. However, the recent testing that's been done is showing otherwise. And so this here are a couple of samples that we had tested, and on the left is about 4 months old, and we can see that it's carbonating into it. The B and C are actually block that we had laying around. They are at least 20 years old. They had to have been more. I mean, the difference between sample B and C is that one of them was stored inside and one of them was stored outside. So one of them was inside above the block plant. It was a shelving unit that had been there for, I don't even know how long, probably 40 years. And same with the block that was outside in the environment. So I guess initially I was curious to see if, being exposed to the elements affected. But as we can see, these samples here are fully carbonated. So this phenolphthalein indicator solution test, I mean, it gives us a good visual, but it really doesn't tell us much, right? Other than neat visual. So I'd like to take a minute now before we go into some of the preliminary testing, is to talk about sequestration potential. I mentioned earlier that roughly 45% of the CO2 emissions for cement production was due to the heating of the limestone, and approximately 43% is chemical reaction. So this heating here, as the cement industry gets more efficient, this is changing, right? So I know that Heidelberg, in their 2019 sustainability report, they report a reduction in CO2 emissions by 22% since 1990, and their goal is 30%. So this number can change, but this one, as it is, can't unless we're talking about the carbon sequestration research that I'm going to go into. I'm going to take a few slides here, and these are the NCMA slides that were presented in Milwaukee. Let's see how I'm doing the time. Good. And it's about the recent work on carbon sequestration. So the indicator solution test I showed you, are, like I said, it's good for a visual, right? But they're actually looking at thermogravimetrical analysis, which is TGA testing, where the raw materials are actually heated up and weighed before and after a certain temperature range. And that temperature range is where CO2 is actually burnt off. And so so we're looking at here is the weights, and when we hit about 500 is when we see it changing, and then to 800. So that temperature range that the CO2, that the carbon burns off at is about 550 to 800 degrees. So they weigh it before and after, and that will give us, and then compare that to the raw materials and how much carbon is actually in those raw materials. So this is how we're getting these preliminary tests. And this is a summary of some initial testing, and So based on that potential of 43%, right? That 43% was that part of the pie chart that was due to the chemical reaction, CO2 given off during the chemical reaction. Initially, we've got 35% of that 43. Short term, which I believe was about 4 months, is 43, and then long term, which was that old block, is 65%. So this block here that had been out in the yard is showing 25 to 28% of the whole sequestered CO2. So where we are now. So NCMA has identified about 6 producers in North America to send in their block, and what they're trying to do is kind of like fine tune this testing method and to see if it's actually going to be a viable way to measure sequestration. And another thing is those that block that I had showed you. I mean, 20 years old plus, right? So we're actually going to try to figure out at what point in time will it be fully carbonated, right? So it's looking like it might be, so they're going to do 4 months, 8 months, 12 months. Hopefully it'll be fully carbonated by 24 months. And then they're also looking at additional testing methods to kind of validate these findings. So the concrete masonry and paver PCR was updated earlier in this year, and it includes CO2 sequestration language. So that will be able to be included in our global warming potential numbers, and it'll be at 28 days for cradle to gate, which is the product stage. And there's also language that will be able to include sequestration during the use phase, which is kind of what that research is based on, is seeing how long it takes to be fully carbonated. So it won't be included in global warming potentials, but there can be language so that it can be concluded by designers for when they're doing like an overall LCA. I could go into this quick LCA, or unless you want to open it up for questions, or you want me to keep going? Okay. So I'm just going to show you a couple of slides on this project that I did, which I took a kind of low-rise commercial building, very, very simple. I only included the wall types. I did not include foundation walls, but I did include, I did include the foundation walls because different building types kind of required more or less concrete in the footing. So I didn't include the walls, but I included the footings because that's the thing that would change. I didn't include openings or floors or anything that would remain constant for the different building types. I did not include interior finishes unless they were required. And this is just a list of things, kind of some of the parameters. And if anybody wants to look further at this at some point, I'm absolutely available. But it looked at A1 to A3, so it's just in the product stage. And I looked at clay brick veneer with an 8-inch cavity wall. And another one of the requirements is that I got as close to energy code compliance that I could with these materials for climate zone 5 where I'm at. So I got brick with block. I've got block veneer with block. I have a full-size ground face with block backup. This is a insulated block, 12-inch. And what's interesting here is that this insulated block uses EPS instead of XPS insulation. And somebody mentioned earlier about how CO2 intensive insulation is, and it's XPS is very, very CO2 intensive. And this here is another insulated block and fully grouted insulated block for high seismic. Here we have brick veneer on an ICF, and then here we have brick veneer on a stud backup. And all of the data I used were from, in most cases, they were industry average EPDs. So I used the clay brick EPD. I used JANDRA specific for the block global warming potential numbers. And just kind of as a side note, my regular normal weight block was pretty much right on with what Athena is reporting for their normal weight blocks. I think that's kind of interesting. And I believe Athena got their data from the Canadian industry average, if I'm correct. So everywhere I used mostly industry average EPDs, except for the XBS is Owens Corning specific. And I think this can be used as a kind of baseline jumping off point. Like, I think that if we're looking at the brick and wood, like it's not that far off, right? Like I think it's being marketed by the wood industry as, being this carbon negative and all of this, right? But it's not that far off from like a, block veneer and block backup, right? And it's because it's not just the wood, right? Like there's all these other things that go along with it. And when we include all of those things, it kind of levels out the playing field. And I think there's a lot of potential with starting off at a point like this when we start adding in the sequestration, right? Like we were looking at over time, those percentages of 25 to 28 as a range. That's going to bring us way down, and it really levels the playing field. That's what I've got, and I'd love it if you have questions, and hopefully I made this understandable.
Yeah, certainly. Thank you. That was fantastic. I think there's a lot, definitely a lot there. That was pretty good. I think for me anyways, I had understood all of it. So I guess I can open it up to questions at this point. I know I certainly have a few. I feel like I did a lot of the talking this morning. So please feel free to pop your questions into the chat or into the Q&A. And I'll get us started here. So I guess a lot of it for me, like when we look at the life cycle and kind of the last slide there, you know what, before I ask my question, I will open it up. We do have someone who raised their hand here. So Mark, you should be able to unmute yourself.
Okay, great. Thanks, Andrew. I didn't mean to jump the line.
Oh, of course.
Heidi, fantastic presentation. Very, very interesting. Thank you so much. I had a question with respect to you're mentioning how long it took to fully carbonate. I think that's great. I was also wondering if it was captured how much they're actually going to sequester. I think that's more of one of the most important things to quantify is how much CO2 will we actually sequester, because as you mentioned are very durable and long-lasting buildings. If it takes 10 years or 40 years to fully carbonate, I don't see that as sort of being an obstacle with the buildings that we create. I was more interested, we did a preliminary carbon sequestration spreadsheet essentially to show designers, but it was loosely based on the Athena data, and I can't remember, something like anywhere between 25 and 35% of the percent weight of cement will, end up being absorbed. The CO2 will be absorbed. I was just wondering if, this new testing that the NCMA is looking at is sort of supporting, are those results sort of similar then to the Athena?
Yeah. So the only, I have preliminary testing just on that block that I showed. NCMA is currently working on, several different producers and their blocks. So I can only speak to what our block showed. And it showed a range of 25 to 28%, and at fully carbonated. So it is somewhere in the ballpark of what you just mentioned. And I'm sure it's going to depend. I'm sure there's going to be regional differences, right? So some different producers have different aggregates that that are going to change these numbers. But so kind of that's one of the things the NCMA is trying to pin down is there regional differences, what they are, and just kind of start trying to get a baseline of that.
Well, that's fantastic. Yeah, that's really great.
Yeah, and it is looking like it's going to be I don't know if I should it's looking like it won't be more than a couple of years before it's fully carbonated. And that's just kind of based on what my feeling is on it. I don't have any data to support that, but kind of looking at some of the testing that we have going on now, like as long as it's not, you know, coated in some unbreathable coating, you know, it'll be within a year or two.
Yeah, for sure. You know, carbonation rates for concrete, you know, but you're talking wet cast are pretty well established. And I guess, like you said, they're can be quicker for the dry cast, which is great. I guess the only thing too is just with respect to carbonation, it is, and you probably already know this, but it's inhibited by your relative humidity, right? If it's really moist, there's not enough room for the carbon dioxide to diffuse, and if it's too dry, there's not enough moisture for it to react with the water. So I think the sweet spot is somewhere around, I think about 70% where you get maximum carbonation rates. But again, I guess I was just looking at that and saying, I don't know if the timeline is as important as how much is actually sequestered. So I think it's great that they're undertaking that study. So sorry, thanks for answering my question. 28 to it's more accurate than the data that we had. So thanks.
Okay, you're welcome.
Thanks, Mark. With that, any other questions? And then Mark kind of stole mine, so where I was going to steal his. So I guess my question, I'd be interested to see once we move out of the A1 to 3 scope or boundary for that life cycle assessment, how we would then compare to the wood backup LCA as well. Is that something that you're moving into, or you just kind of have it shelved right now?
Yeah, I mean, it's what I've done is actually kind of do a couple of different scenarios, right? Like it's all you can really do, right? Because it's impossible to tell what is actually going to happen. But, you know, so I mean, in my own research, I've done just a couple scenarios where actually at the end of life, that wood is actually put in a landfill, right? Because most of it ends up in a landfill. It's either burned or it ends up in a landfill. And if it's, you know, one scenario, if the wood end up in a landfill, is that it's decomposing underground and it turns to methane, right? Like, is any, you know, like that's one scenario, right? And then where are we? You know, with that being 27% more of a potent greenhouse gas. But I guess best case scenario, it gets combusted, right? It turns into pellets. So it definitely is not stored impermanently, and it's certainly not carbon negative. So I think there's a lot of things to be uncovered. And I think that the best way to do it is just like pick a couple scenarios, right, that are fairly neutral and just look at the data and then, you know, and then go from there. I mean, that's kind of the approach that I've been taking. Right.
Yeah, certainly. There's lots of ways to go about it, and a lot of questions still to answer. I think certainly that's something we've kind of started the right pathway with these discussions that we've been having, but there's still a lot of question marks out there for sure. So certainly look forward to seeing the research that comes out of the NCMA study. All right, is there anything else for Heidi at this point? No? Okay. Well, with that, certainly would like to thank you for your time this afternoon. It was very informative. We're quite lucky to have you in the industry here. It seems like the work that you guys are doing is certainly very cutting edge, and I hope that this isn't the last time that we'll be able to engage with you as a group.
All right, thanks for having me.
Thank you. All right, so I'll give everyone 5 minutes here, 5-minute break, and then we'll get into our final session of the afternoon with Dr. Hagel. So we'll be back at 2 o'clock. So everyone just take a quick break and join us back here in 5 minutes. All right, well, welcome back, everyone. I'm just confirming. Oh, Mark, you're back. Perfect. So I will stop my share. So definitely grateful to have Dr. Hagel here from the Alberta Masonry Council, who is also one of our sponsors this afternoon. Dr. Hagel holds a Bachelor of Science in Architectural Science and Applied Mathematics, a Bachelor of Science in Civil Engineering, and a Doctor of Philosophy in Civil Engineering, all from the University of Calgary. Prior to employment with the Alberta Masonry Council, Mark worked for the Canadian Concrete Masonry Producers Association. He then moved on to the role of a building envelope engineer and structural engineer with the Calgary office of Hallcrow Yawlis. Mark's thesis dissertation, service life prediction of connectors and masonry veneer wall systems, was heavily rooted in building science and structural engineering. Mark's fields of expertise include thermal and hydrothermal modeling of building systems, corrosion modeling, life cycle cost analysis, structural analysis and design, and the durability of components. In 2018, Mark served on the National Research Council of Canada's working group that developed the guideline on design for durability of building envelope. Mark has also taught first-year engineering courses as a sessional professor at both University of Calgary and Mount Royal University. So with that, I will pass it over to Mark, who I know has a very compelling presentation for us this afternoon. So thank you, Mark.
Awesome. Thanks so much, Andrew. Thanks for the invite to come and speak. I'm just going to try and get this presentation shared here. Give me a second. Are we able to see the screen?
Yeah, we're good.
Awesome. Well, thanks again for letting me come and speak, and thanks for the invitation to attend. I'm following three amazing presentations, which is hard to do. I kind of feel like everyone in the audience here has sort of stepped out of like the latest Marvel Avenger movie, and now I'm following up with like a documentary on ground squirrels or something. So I hope that you find the presentation somewhat interesting. Moving along, I'll just go quickly through outline or agenda. I'm going to talk about net zero energy target and net zero carbon targets, just so we have an idea of what we're aiming for. Then I'm going to discuss reducing our carbon and energy footprint of masonry through innovations in our masonry materials and through more efficient masonry and assembly design. And lastly, discuss sustainability of masonry assemblies through more accurate thermal modeling, and finish off with the durability of masonry products and their contribution to sustainable construction. So maybe at the end of each section, if you want to ask questions, I know it's kind of hard if you're trying to remember your questions till the end, we can always do that too. Anyway, I'll start it off here. So the National Energy Code for building requirements, as Gabby pointed out, they're in line to meet the net zero targets that have been mandated by 2030. So the National Energy Code for buildings in the provinces that have adopted it are moving to this net zero energy in buildings by 2030. And they want to be carbon neutral in buildings by 2050 for new construction, and aim to retrofit all existing buildings in Canada to net zero energy by 2050. So one of the ways we do this, we're predominantly looking at walls when we're talking masonry. So one of the ways we do this is passive house. So the passive house requirements basically specify an R value that you must achieve out of your walls, roofs, etc., in order to have a net zero energy building. So passive house basically is saying you need to achieve R38 or higher after you account for thermal bridging losses. So thermal bridging losses could be, thermal bridging at a corner of a wall, at a linear transition between above grade and below grade walls, at a roof junction. So basically when you account for all these, you're really looking at about R45 or higher as far as your insulation value in order to achieve passive house requirements. So we're not the only industry sort of facing these these targets, of course. So with wood walls, you know, they're likely going to have to be double studded, 2x6 walls, and a 2x6 wood wall and a 2x4 wall, maybe for the cladding. Their approximate depth is going to be 12 inch to 15 inches. And again, this will give you approximately an R48 to R51 insulation value. So that's a good number to remember, 12 inches to 15 inches, because part of what we want to do in order to stay competitive is make sure that our walls are not unnecessarily thick. So let's talk about reducing the carbon energy footprint of masonry through innovations in masonry materials. I think this has come up a couple of times. We can reduce the carbon footprint of our clay brick in its manufacture by having larger cores. So our current CSA requirement A2 requires that exterior grade brick be 75% solid. This is in the National Building Code and also in the brick standard, CSA 882. If we increase the core sizes, which is going to reduce the percent solid, we can have a significant impact on carbon savings. So larger cores allow the firing time in the kiln to be less, and it uses less natural gas. And again, I guess as another possibility is you could start looking at alternative fuel sources to natural gas, such as hydrogen, to further reduce the carbon footprint. But if you just use traditional natural gas and fire your brick, this 5% reduction in the gross cross-section area can be estimated to drop the CO2 required to produce the unit by about 0.2 kilograms. So a rough estimate of about 410 million bricks sold annually in Canada would produce 6.3 million less kilograms of CO2 per year, just by increasing the core size so that you have a 70% solid unit instead of 75. That's equivalent to taking 1,300 cars off the road for a year. Using a core size with a correlating to 65% of the net gross area, you'd basically be double that. And you're looking at almost 13 million kilograms of CO2 less per year, just by making the cores bigger and reducing the firing time. The other thing that'll help reduce our carbon footprint with a larger core is that the units are lighter, so there'll be less weight and less fuel consumed in transport. And the larger cores translate to more mortar in the cores and less clay. So as Heidi pointed out, cementitious materials absorb carbon dioxide, whether you want them to, they absorb carbon dioxide. And the clay brick doesn't, but the mortar does. And as you can see on the picture on the right-hand side, as they press the brick down, you're going to get more mortar into those larger cores. So reduce carbon footprint with larger cores, there's obviously the business case for it. As an earlier presenter pointed out, you're looking at a 400% increase in the carbon tax from 40 to about 170 per ton of CO2 by 2030. So accurate EPDs and larger cores in our clay brick will help reduce the taxes we pay. So another alternative we can do for the concrete block in Canada is to recognize, do the research and recognize a better F'(M) value. So F'(M) is our material strength of our masonry assembly. It's basically when I put the concrete block and the mortar, I put it all together and I measure its strength. That's the value that engineers use to design. Our current table in S304 contains F'(M) values that are based on 40-year-old testing data. Recent testing at the University of Calgary suggests a 33% increase in recognized strength just by testing with with units that are manufactured today. So basically what that's saying for us is that our 15 MPa block can be considered a 20 MPa block, and a 20 MPa block can be considered a 30 MPa block. The US already has even higher recognized strengths than this table that you see on the right-hand side that we're using in Alberta. And they've been using these improved F'(M) values for about a decade. So what does the F'(M) value do that helps us out? Well, we can use smaller block. It translates to less grout and concrete going into the cores, and less steel and rebar in the wall because your strength of the actual masonry itself is stronger. So in particular with tall walls, translates to being able to go taller, but using a smaller block. So being able to use an 8-inch block to go the same height you normally go up with a 10-inch block. Here's a really good example from an actual school, and this is addressing this issue with underappreciating our strength. So this is a school in Alberta, and highlighted in red, this wall has two 20M bars in it, and I'm speaking a little engineers here, so I apologize, but it has two 20M bars, which is basically the biggest bar that we put in, one size smaller than the biggest bar we put in walls in Alberta, and it is at about 2 feet on center, or 600 millimeters on center. Now, this wall is actually not 36 feet tall. They have a steel post and beam structure, and you can see about the 12-foot mark that the wall is laterally supported. So the true height of the wall is only about 24 feet. So this underappreciated F prime M value, if I run through our math software, which is developed by CCMPA and CMDC, I can use a 30 MPa block with two 20M bars at 800 on center and eliminate the steel posts altogether. I can just bare the roof instead of on these steel posts. I can bare it on our block wall like it should be. So same size block wall, 12-inch, but I'm also, by not having to use bars as frequently at 32 inches on center instead of 24 inches on center, I'm also saving about 1.2510 M bars and about 2.93 meters cubed of concrete per meter of wall that this over-designed wall is not saving. And I can still go the 36.5 feet that is required. So better recognizing our strength will help with our reduction in our carbon footprint and more efficient use of our materials. So moving into our masonry materials and their R values and how we compare it to other materials. So a 4-inch clay brick, R 0.4, solid concrete brick, R 0.23, a hollow architectural concrete masonry unit, R 1.36. So for comparison, hardy siding 0.1, vinyl would be about the same, a little bit less, stucco at a point R 0.097. And if you're using EIFS, it'd be somewhere between R8 or R10, depending on whether you're using expanded polystyrene or extruded polystyrene. So that gives you an idea of some cladding materials that are competitors to our masonry products and where their R values lie. On the structural side, if I look at block, 8-inch block, it's R1.8 if they're hollow. You might have a bar at every, a meter on center or something, and wherever else you just leave it hollow. If it's filled with vermiculite, you hit R4.6. So a 10-inch block, R1.9 and R5.6, and a 12-inch block, R2.3 and R6.0. So these values are straight from the NECB user's guide. And an important thing to note is these are their lightweight units. If you use normal weight, those values decrease a bit. So on that, and looking at ways we can keep our original configurations of traditional block and just increase their R value, using a lightweight block class C versus normal weight block class A, you gain R1. And if I go to an even lighter weight block in class D, I can gain R2. If I'm looking at architectural units and I want to use aerated autoclaved block, I could have an R4.5 sort of brick equivalent sized block unit. So insulated clay brick, as we mentioned, it's only R.4. I found this on LinkedIn. It's a really unique way to insulate a clay brick. So they use plastic molds, ABS plastic that's recycled, cast it into a mold that looks like Lego, and they have a fired clay brick hollow shape that it inserts into. And it's currently being developed by Farmore Architecture. Mostly I put it in here as things that we may be able to do to modify and improve our units to get better R values out of them. The other thing we stumbled across a couple of years ago is an insulated concrete masonry form. That's how I would coin it. The product's called One Step, and here you can see it on the left-hand side with a nice glass of wine. It's basically concrete masonry face shells that are tied together with plastic webs. So like an insulated concrete form, except your face shells are concrete masonry instead of styrofoam. So you would have a fully grouted wall essentially, but the walls that I see where structural masonry is being used these days are, the spacing is usually 400 on center, so it's basically fully grouted anyway. So these units can have an R value of R20 to R35, depending on the size and the insulation. And because the thing that weighs is the concrete face shells, the webs don't weigh anything. It doesn't really matter if it's 14 or 16 inches wide, it weighs about as much as an 8-inch block. So it's less heavy for the masonry to lay, or mason to lay, and has the potential to help us meet these net zero energy targets, either as it's just a backup wall or even possibly lead to single wide masonry being buildable in Canada again, because currently it really isn't with the R value targets that we need. So just to give you an idea, a wood frame wall 2x6 with R20 bat in it is about R16. And if I'm looking at a 12-inch, well, let's go 8-inch block that has vermiculite in it, I'm at R4.6. So we're about, a quarter of where we need to be in our backup walls. So did we want to ask questions or save them for the end? I'm sorry, I can't see. I can just see the slides.
Yeah, it's okay. Is there any questions for Mark at this point? Or we'll just save it for the end, potentially, yeah. Okay, we'll carry on, and then
just keep
maybe
rolling.
We'll
okay.
open it up at the end, and then I guess if anyone has any questions, just use the raise hand option or just pop it into the chat throughout.
Yeah, I apologize. I talk really fast. I drink too much coffee, and so if I need to slow down, just let me know. Other ways we can reduce our carbon footprint and increase our energy performance is through more efficient masonry assembly design. So I look at, I'll give you an example here. One of the ways a really straightforward way is to have continuous insulation. So you're actually allowed to design without insulation or with non-continuous insulation, but really does end up hurting your overall wall performance once you have to start accounting for thermal bridging at your linear transitions. So at a grade, at a floor level where a shelf angle is, right? So just actually putting a shelf angle at floor level gains you R2 per floor, and it'll gain you R4 at grade and R2 at a parapet. So you can basically gain about R8. So shave off 2 inches of wall depth, or wall depth and insulation depth, just by using a standoff. So one of the advantages of that, and I think it was brought up by Gabby, using insulation unnecessarily, especially when it's either expanded polystyrene or extruded polystyrene, it's actually detrimental for the environment, right? So obviously we want to make sure that we're using the right amount of insulation to hit our energy performance targets, but we don't want to be excessive. So incorporating, just to kind of solidify this, incorporating shelf angle thermal breaks. So on this particular example, straight out of Morrison Hershfield Thermal Catalog, which is online, I have an R15 exterior insulation, about 3 inches of extruded polystyrene, directly bolted shelf angle. You have this linear thermal transmittance, the 0.464. You don't have to remember that number, but treat it as the baseline. If I go to a double knife plate, usually it'd be single for the record, I get a 30% increase in the thermal performance. And if I take that knife plate and I choose a different standoff material, so thermal performance of different materials, aluminum, highly conductive, which is why they make beer cans out of it, because it gets your beer cold faster. Steel, about a quarter of aluminum for thermal conductance. Stainless steel, a quarter of steel. But GFRP, so glass fiber reinforced polymers, kind of like the fiberglass on your boat, they're at 0.5 watts a meter squared. Okay, so about 100th of steel. So sometimes when you change the material, you get an even more significant reduction. So there's a product called Armatherm. It's an FRP standoff. This one's already modeled in the Morrison Hershfield Thermal Catalog, and it ends up giving you a 60% increase in your thermal performance, dropping your linear transmittance to 0.186 from 0.464. So other things we can do is take a look at how we build our walls. So it's typically popular to use an embedded tie block out here where we are anyway, when we're building schools. They use these embedded tie block ties. tie the brick veneer to the concrete block. Particularly with these ties, if you change the material to something like stainless steel or FRP, there's a significant increase in the wall performance. So I'm going to take this as an example here where I have an 8-inch block wall with R25 insulation on the exterior. And it drops down with these embedded galvanized steel ties to R15. Now, one of the reasons it does that is you're driving the cold further into the wall with this embedded tie by about 6 inches. So if I switch the tie configuration instead of being embedded to a surface tie configuration, there's some great things that happen. So the surface tie here doesn't drive the cold as far into the wall. So if I look at this R25 insulation, the same example, just by using a galvanized steel surface tie, I move to R18.5 from R15.4. I gain R3, so about 3/4 of an inch of insulation. Now, if I move that and make that a stainless steel surface mounted tie, which actually works really well with block, because unlike a galvanized steel stud where you have to worry about corrosion with dissimilar metals, I don't have to worry about that with block. I can move to a stainless steel tie, and now I've gained R5. I'm at R20.2. And if I make that GFRP, I've basically gained R7. So just simply changing the configuration to surface mounted makes a big difference. And surface mounted in stainless steel, I can basically take an inch of rock wool or an inch of extruded polystyrene off that wall and get the same sort of thermal performance as using that same depth of insulation. So I think that's a real indicator that we can still work within some of the traditional things we use to build masonry assemblies and enhance our thermal performance. So adhered masonry veneers, they might be a little bit more popular out west. I think they're going to become more popular as the National Energy Code for buildings restrictions become tighter, because you will be putting more insulation on the walls. So where you might have had 3 inches of rock wool insulation, you might now have 6 inches. So you've just lost that 3 inches you had for your brick. So on the left-hand side, we have a steel stud assembly and an adhered stone veneer on a cement board. And on the right-hand side, we have a wood frame assembly with thin brick on wood frame. So these details, again, already exist in the Morrison Hershfield thermal catalog. If I have 7 inches of extruded polystyrene, no insulation between the studs, I can use these Armadillo thermally broken fiber reinforced polymer Z-girts, and I get a clear wall value of R35.5. So I haven't lost any of my R value to thermal bridging. I can do the same thing with a iso clip, which is a plastic shim behind a metal clip for this iso clip system. I put in 8 inches of mineral wool and I get 33.6, but it actually, my clear wall in this actually drops down to 31.5 because these clips are not as thermally efficient as the FRP Z-girts. And then if I move to a thermally reinforced or fiber reinforced clip, again, 8 inches of mineral wool, but this time I don't really lose any R value. Again, this Cascadia clip, it's thermally broken fiberglass clip, and it gives you better thermal performance. What this is showing us though, is that we have already available on the market I think the materials to meet net zero as it moves forward. So another solution that speaks a little bit more to the assembly is our shelf angle layout. So for masonry walls installed to a height of 36 feet, you can bear off the foundation either on a shelf angle on standoff or on a brick ledge, and you don't need shelf angles floor to floor. So this reduces the thermal bridging effects at your floor levels. All linear transitions have to be accounted for in the thermal modeling. And it also reduces the highly CO2 intensive material like steel. So it reduces cost, and it also reduces our footprint by not using as much steel on our buildings. So there is only one thing to note: when you do this, you do have to account for differential movement. If it's a wood frame building, because wood frame shrinks and clay bricks swell when they get wet, and does have some differential movement. So here I have a shelf angle layout where it's a shelf angle at every floor. So instead of I'd have an at-grade transition and 1 to 3 floor transitions. I can do this, then I don't really have to worry about differential movement on this wood frame structure, but I can move to bearing up 30 feet, having a single shelf angle at the 3rd floor. And then I've reduced 2 linear floor transmissions. And I do have to account for this larger differential movement at the windows and the shelf angle, but it can definitely be managed. So this is another way that we can, in the design phase, get better thermal performance out of our walls. So I'll move on to improving sustainability by improving accuracy of thermal modeling. So why is correct modeling and energy efficient assembly selection so important? Well, as I'd mentioned before, to save using insulation unnecessarily. We want improved thermal performance, but if the building is not actually benefiting from the additional insulation, then it reduces the environmental impact, especially when we're using extruded polystyrene, expanded polystyrene, spray applied polyurethane foam, all of which are oil products that are carbon intensive to produce and do not break down for centuries in landfills. Less insulation reduces the cost of our masonry and veneers and makes it more competitive, and reducing the thickness of the exterior walls increases usable interior space. This is especially important when property lines are restrictive. So if I'm building a school, it doesn't really matter if I have a 20-inch wall or a 22-inch wall. I have fields and everything around, but if I'm looking at building a mixed-use residential building and I have tight property lines, if I can only go inward with the depth of my wall, then I'm going to lose interior space and probably lose out to a competitive wall system that can be thinner. So one of the things we can do in order to increase our accuracy in thermal modeling is to use the prescriptive trade-off calculator available to us through the National Energy Code for Buildings 2017. Now, they have talked about eliminating the trade-off system, but I don't know if they will anytime soon, partly because it's actually a really fair system that was essentially developed and pitched by Gary Sturgeon from our industry, one of the technical gurus in our industry, who basically said, if I have a wall that I'm allowed to have 30% glazing at R2, then if I want to use less windows, then I should gain the benefit of not having to use as much insulation and the same sort of insulation demand out of my walls because I've used less windows. So we don't all want to live in bunkers. For sure, we want glazing, but glazing never translates into a high efficiency from a thermal perspective. So we should be allowed a trade-off because you're going to basically get the equivalent performance. The more glazing you use, the less thermally efficient your wall will be, regardless of how much insulation is stuffed into the opaque portions of the wall. So the National Energy Code allows you to trade enhanced energy efficiency for one component against decreased energy efficiency from another component within the same part of the NECB. And in 2011, you could actually change the orientation. So in other words, I could stack the roof full of insulation and reduce the insulation demand on the walls. Well, they've eliminated that in NECB 2017. So now it has to be in the same orientation. So in other words, I can trade off lower insulation or lower insulation efficiency levels on my west elevation for higher efficiency levels on my east elevation or something like that. But I cannot trade against the roof or lighting or HVAC. So I think it's best, that's a lot of words. I think it's best to see it in an example. So here we have a brick veneer wood frame building. You have some aluminum windows here. From the actual takeoff, the building's 40 feet long and 30 feet high. It's about 1,200 square feet. I have about 207 square feet of windows and 42 square feet of doors. So in total, I have 249 square feet out of 1,200 square feet. That is fenestration and doors. So this building in Edmonton is allowed 32.5% being glazing at R3, which is the prescriptive value in the National Energy Code for Buildings for this climate for Edmonton. So I'm allowed 32.5, but I'm actually only using 20.8%. So I created this spreadsheet to try and figure out the trade-off system, and it works quite nicely. In the purple, you can see the prescriptive requirement, and it's basically saying, If I have my walls at R27 and my fenestration at 3, under the prescriptive path requirement for this building, it will consume 85 watts of energy to heat it. That's how much heat loss will be through your envelope. So what happens is once you've picked your windows, if you play around with your wall R value until it gets close to this 85 watts. So the bottom box here, 85 watts a K. If you're 85 or below, it means you're using less energy than the prescriptive path and you're okay. So what has this done for us? It has gotten this wall system down from R27 to a requirement of R18.3. So the next step is to thermal model it and account for thermal bridging. So again, I'm not going to get too detailed. Just want to show you the outputs. These values come off the Morrison-Hershfield guide. You'll notice that in this Morrison-Hershfield guide, they did a very good job. They have a ton of details, but they don't have every possible detail. So what they have in this guide right now is a detail for a shelf angle directly bolted to the foundation and a shelf angle directly bolted to the wood floor system. So if I put this into the BC Hydro thermal performance spreadsheet, we have a clear wall value of R28 with all the thermal bridging of this at grade transition, which is not on knife plates, and the second floor and third floor the same, drops down to R17. Now, using an improved detail, a significantly improved foundation detail where it's on knife plates, I go from I basically get a 393% increase in thermal performance. And I get about 148% increase at the floor level. And that translates from my wall going from a clear wall value of 28.4 to 22, which is above the 18 that I need, simply by building it the way we'd build anyway, to be honest with you at this point. There's continuous insulation above grade and below grade in Alberta. At this point, I haven't seen buildings without it. So just by simply having the right or more accurate thermal models we've had that reflect how it's actually being built, we have a significantly improved thermal performance and didn't end up adding an inch of insulation to gain R1. So again, a good example here, we have a school gym wall, and this is why this is so important. This school gym wall is a 12-inch block wall. It's got 5 inches of rock wool insulation, so about R21, and airspace and 4-inch brick. Total depth is almost 22 inches, 21.5 inches. And it's calculated to have an R value of R16.1. So if I look back for a second, I look at this portion of the gym wall, and there are no windows, there are no floors because it's a gym wall. There's only a parapet and at-grade transition. So I look at that and say there's something that's a little bit off with the modeling. So if I use the details that are currently available to us from this Morrison-Hershfield online catalog, they don't have 12-inch block, they only have 8, but I put in all those numbers and I get something like, and they don't have a block wall with brick veneer on knife plates at grade. So I put in these values and I get down to R17.3, which is still about R1.2 greater than is estimated in the detail. But again, the wall is actually 12 inches, and you can see on the very bottom of a wall, the shelf angle is on knife plates. So if I account for those two differences, my clear wall value is actually higher. It's R25.5 because it is 12-inch block, not 8. And with the more accurate thermal models, I drop down to R19 instead of R16. So we basically, again, gained R3 on a wall, or saving yourself 3/4 of an inch insulation. So that's great to know. It's also good to know how our other traditional ways of building are performing. So there were concerns with insulated brick ledges. Are they not going to meet sort of the values that we need in order to have net zero? Actually, it's interesting to note that there's only about a 1.2 R loss from using a shelf angle on knife plates versus a standoff. So if I look at the baseline where it's directly bolted to the foundation, if I put it on a knife plate, there's a 75% increase in the thermal performance. And if I put it on an insulated brick ledge, then there's a 68% increase in thermal performance. So not far off that of a knife plate. because the knife blade, of course, is steel and more thermally conductive than concrete. The other thing the industry could do is entertain the idea of using more an insulated brick ledge from the ICF industry. So maybe there is a product we can develop that just sort of tacks onto the top of a foundation wall and provides you with this insulated brick ledge. So that's a possibility we could entertain as well. So I thought I'd finish off this section with giving you an idea of the impacts of the insulation and thermal modeling and trying to hit net zero targets. So what you're looking at in this, this table here is what is going to be required as far as insulation and thickness in your wall in order to hit net zero. So we're starting off with wood stud, and you'll notice here we've got brick veneer. We have 5 inches of extruded polystyrene. The total wall depth is about 5.5 inches when we use a 3-inch brick. It's going to be about 16 inches if we use a traditional 3 5/8 inch brick. If I look at a insulated wood wall double studded, I'm going to hit a target of R51, and it's going to be about 15 inches in depth. So I can tack on a siding product, I can tack on stucco, I can tack on adhered masonry veneer, and you know, that's going to affect the depth a little, but not much. It's going to be somewhere around 15 inches. And then the final one that I could find in the Morrison Hirschfield catalog was metal panel on wood stud. There was no EIFS values for wood stud. And again, you're at the 15-inch depth. But actually, this is like a win-win story and an opportunity for us. Because what this is showing us is that with a wood stud wall and a 3-inch brick, we can hit net zero targets and be approximately the same size as a wood wall clad in something else. So if I move to a steel stud assembly, if I look at the brick, you know, it's going to be 18 to 19 inches as far as the thickness of the wall. We're looking at basically, because it's a steel stud, you're going to need about 30 R30, so about 6 inches of extruded polystyrene or 7 inches of mineral wool. If I look at maybe an adhered masonry veneer or siding over the steel stud and the Z bars, the fiberglass Z bars, we're looking at anywhere between, well, about 17.25 inch in depth. If I look at EIFS, this is where we have a little bit of difficulty competing. So EIFS with steel stud and foam is going to get us only 14 inches. So 3 to 4 inches less depth than, or sorry, 4 to 5 inches less depth than our brick walls. And of course, as you probably already know, they have stamps to make EIFS look like brick, so to give it that brick pattern. So that's definitely something we are going to have to look at. And then finally, the steel stud and metal panel wall, it's going to be approximately, you know, 18.5 inches at largest. So we tend to be okay for claddings other than EIFS in the steel stud category. Finally, with concrete block, this is where the walls get fairly large. You're basically going to need about R35, so 7 inches of extruded polystyrene or 8 inches of mineral wool to hit our net zero target, about R50. So that wall ends up being with an 8-inch block and a 3-inch brick, 19.5 to 20.5 inches deep. If I take a concrete block wall and I want to attach siding to it or an adhered masonry veneer, then I'm going to be anywhere between 18 and 19.5 inches, so approximately the same. And if I go to metal panel, I can achieve these net zero targets with a 16-inch wall. So yeah, I think this just gives you an idea of sort of the depths we will have to go to achieve net zero. So I'm definitely flying through this. We're kind of getting close to the end here. So one of the great things about masonry is that it's very durable, and that actually already contributes to sustainable construction in a very passive way. So very famous quote, the greenest building is the one that is already built. So Carl Elefante, he was an architect. If it doesn't wind up in a landfill, it's going to be better for the environment, or if it can be recycled, etc. So buildings should be durable and built best to last. I'm borrowing that from Masonry Works. Long service life for buildings should be mandated by authorities having jurisdictions. We've already seen that at Alberta Infrastructure. They're mandating a 75-year service life for their structures. And that means you're going to have to use materials that are durable, highly resistant to methods of degradation, fire, and in particular impacts as well. So we also want to make sure we're using materials that are easily recycled or reduce construction waste at time of construction, like modular brick and block. And of course, anything that has a smaller carbon footprint. So our external environment has a huge impact on durability, energy consumption, and cost. You know, what works in Calgary does not necessarily work in Vancouver, in particular with the envelope components, right? So I can use a mill galvanized tie and it'll last 40 years as a brick tie in Calgary. It'll last about 10 in Vancouver. So what works in one place doesn't necessarily work somewhere else. So Canada, of course, has a very diverse geography. We have Great Lakes, desert, marine, rainforest, Arctic, prairie, mountains. So each geographic region is going to require, you know, different levels of durability. But the ironic thing is the one thing that crosses all those boundaries is masonry. Masonry works in all of those environments as far as being durable. So traditional structural materials, if I look at their durability, we have wood, masonry, concrete, steel. I could probably add aluminum and glass to that, but we'll just stick with these four. So if I look at a quick durability comparison of the structural materials, most durable would be reinforced concrete and masonry, and then less durable steel and SPF wood. So why? Well, because reinforced concrete and masonry, they don't mold or they don't degrade with water. Steel will rust and wood will mold or rot. And of course, steel and wood are more susceptible to fire. So if I look at a quick durability, a comparison of common cladding materials, most durable, full bed masonry veneer, metal panels fairly durable, stick frame and unitized glazing is fairly durable, fiber cement board siding, so that's a mixture of concrete and wood pulp, like hardy board, that's fairly durable. Drained adhered masonry veneers, if they're drained, they have better water management performance, and they're fairly durable. Same, they'd be equivalent to say EIFS or stucco that is drained. Vinyl siding, not as durable. You get a hailstorm and you get a bunch of holes punched in it. And then face sealed stucco might keep out the hail and it doesn't burn, but it does tend to transmit water and cause mold and rot if it doesn't have a drainage mat behind it, if it's face sealed. So how is masonry going to contribute to sustainability? Well, I can clad a building with a less durable structure like timber or steel with a highly durable material like concrete or masonry and significantly increase the durability of the building and its resultant service life. There's a number of timber post and beam buildings that are wrapped in brick veneers that have lasted over 100 years. What I can't do is take the least durable material on that durability chart being stucco and the least durable material, structural material being timber, wrap that timber in stucco and expect the same sort of service life. So great thing about masonry, it manages moisture. Masonry stores moisture. It does not mold, rust, or rot. Because it doesn't degrade with water and both brick and concrete masonry units are absorptive, they actually have the ability to aid in stormwater management. If you look at glazing, you know, glass towers downtown or siding, it basically sheds water onto the street and into your stormwater, whereas clay brick and concrete brick will absorb water, or concrete masonry units will absorb water. Masonry has a high impact resistance. On the left-hand side, videos tend not to work on Zoom. So on the left-hand side, you're seeing the end result. You have a potato cannon essentially firing a 2x4 at a drywall wall. If I wasn't doing what I'm doing now, I want this guy's job. It looks like a lot of fun. And on the other side, we have the same test, and you're watching the impact of this 2x4 as it splinters against this concrete masonry wall. So high impact resistance. Now, this is really important for interior walls, particularly in hospitals and schools where gurneys bumping into walls or students being hard on walls really does impact, you know, the life cycle cost or life cycle assessment of those walls. You know, you can patch drywall fairly inexpensively, but it's material and inconvenience to do that. As was mentioned by Heidi, masonry assemblies absorb carbon dioxide. We created a carbon calculator a couple of years ago. I believe we based it on 30% absorption rate. So this might be a little high, but cement products reduce greenhouse gases over time, whether it's concrete block, grout, manufactured stone products, mortar, scratch coat, cement boards, they all absorb CO2 over their service life. So for a school in Calgary, we did the takeoffs of the wall areas that contained concrete masonry and brick and interior block walls. We're estimating that 63,000 tons of carbon dioxide will be removed from the atmosphere over the life of this building. And that takes 13.5 cars off the road for a year or 6 homes off the grid for a year. So masonry products on the sustainability side of things are also better than some alternatives like steel, which is carbon intensive to produce and doesn't absorb carbon dioxide. So, I mean, we're not trees. We don't breathe carbon dioxide. Like masonry products don't breathe carbon dioxide, but they do absorb it. So aluminum, steel, they don't, of course, or glass. So masonry also is fireproof and offers passive fire protection. And again, this is another important key portion of durability, is the fact that it won't burn down, particularly in condos. You know, condo boards are notorious for not always maintaining all the components in a building. If you want your sprinklers to work on the 5th story of your 5-story wood frame condo, then there has to be pumps, because the service water coming in at 30 PSI is not enough for the sprinklers to run effectively in the event of a fire. Whereas concrete block is going to be fireproof. And you can see in this picture, the elevator shafts and the firewall that stop the fire from spreading. And finally, again, I'm probably preaching a lot to the converted here, but masonry products are green materials. They're fully recyclable. They're modular, so there's less construction waste. You know, they actually grind up the brick and it becomes the black flecks in new brick, which they call grog. And concrete block is ground up and used as either road crush or aggregate in new concrete. And the ties, shelf angles, and rebar are all fully recyclable. So you're looking at a system that's basically cradle to grave. Cradle, it's not even cradle to grave. So, you know, in contrast, something like vinyl siding, it has a low insulation value. It is susceptible to impact and is combustible. It also is carbon intensive to produce and not easily recycled. I don't know, one might even be able to consider it a single-use plastic. So in conclusion, sustainability of masonry. Masonry wall systems have the ability to adapt to meet net zero energy targets for passive house and reduce carbon footprints through innovations in masonry unit configurations and material of manufacture, thermally improved masonry assemblies and more efficient materials and components, and more comprehensive and more accurate thermal models and modeling by designers. And in closing, the highly durable nature of masonry walls already passively contributes to sustainability through long service life buildings that absorb CO2 and fully utilize and are fully recyclable masonry units. So I know that was pretty fast. Just wanted to say thanks, and then I can take questions.
Awesome. Thanks, Mark. And yeah, you got it. That's a lot to cover in an hour. So good work with that. I think we do have John, I believe, has got his hand raised. So John, you got the floor here if you want to ask a question.
Sure. Hey, Mark.
Hey, John, how are you?
Good to see you. You're a great communicator. That was a great presentation, by the way. Couple of quick questions. One is, certainly when we're out talking to municipalities around their climate action plans, they're focusing as much on adaptation as they are mitigation.
Okay.
We had so two questions. One is, I'm very interested by your comment that masonry absorbs water versus repels it. I wonder if there's any data available to understand what that kind of number is, so that way, because that's something that I think will be interest municipalities, because they're very interested in figuring out stormwater runoff. And then the other one was when I think, Andrew, you and I was it the city of Toronto that we were talking to, that they were interested in the thermal mass properties of masonry, because they're concerned about power outages and the swings in temperature that happen inside, that can happen inside buildings, that for the, I think it was the city of Toronto, that's resulted in costing them a lot of money, because if there are outages for long periods of time in condos, people actually have to move out for but when I see all the insulation and sort of all the wall assemblies that you're talking about, I don't understand that relationship, and whether or not it's something that is an advantage for masonry.
Yeah, I think both areas are probably a little bit under-researched. I think what led me to the conclusion that masonry would absorb more water, stormwater, is just, it is very absorptive. And I saw a presentation by a researcher that used to be at McGill and is now in Switzerland or something. And she was modeling wind and rainwater through a downtown core, and how much water was being sort of absorbed or put into the cladding. And she had different claddings. And I just thought, like, that's a really good point, that we have never really looked at that. But glass, of course, is going to shed more water than something that gets wet. And I mean, the National Research Council a good 20 years ago was worried that with their hydrothermal models, the masonry sort of would get wet and took a long time to dry out. So that was basically indicating that we are absorbing a lot of moisture. So the reality is, I think, they're having issues with this one-dimensional model, not modeling venting of an air cavity, which helps dry out your masonry. Right. But the positive side is that it's modeling water absorption and how much so I think it could be quantified. It just hasn't been done yet. But I think there's strong evidence that I could probably even ballpark it if I had to, as far as how much water it's going to absorb over a year of rain events. Yep. With respect to the thermal mass, I think it's under-researched as well. I mean, they're doing a lot of work towards thermal mass, and I'm glad they've got some of it sort of hammered down. I think I'd be interested to see, because I haven't seen any of the data, maybe they've already done it, but if we heavily insulate our walls with 8 inches of insulation, are we losing the I guess the advantages of thermal mass by essentially insulating that concrete block wall from absorbing that extra energy, right? I'm not sure about that. Yeah. Like the brick I think the brick helps. I mean, if you look at it, your brick is going to, as your brick veneer, it's going to absorb the heat and it's going to radiate it into the cavity. It's going to keep the insulation warmer, which means there's going to be less heat loss from the interior building for that reason. But at the actual structure of the building, I don't know if the thermal mass is getting the same sort of benefits as if it was in direct sunlight. So I don't really have an answer for that, but
I thought it was a super interesting question.
It is. It's a really interesting question. And I think, that sounds like something that the NCMA might even already be working on, because they tend to be ahead of the curve on these things. So
thank you.
Maybe Heidi knows. Yeah.
It was actually a study that was being proposed that is currently tabled on this exact thing for highly insulated buildings and how thermal mass affects that. So.
Thanks, Heidi.
Yeah, thanks.
Yeah, that'll be good when there's always great work being done by the NCMA. So I know on the thickness side, and I know when we kind of presented it with for block, if those blocks were insulated, what would the thickness level, like how much would that come down? Obviously a 21-inch wall, particularly in these like markets, is pretty thick, right? So what would insulating do?
I think it's only thick if you're not if you're not talking about like a school, or depending on where, you know, like a hospital lands or something like that, it may not be an issue. But if you're looking at like a multifamily residential building, they should fill them with vermiculite. You're going to basically gain about R3 from the vermiculite. Now, that's the National Energy Code for buildings. I don't know if they did testing that comes straight out of their NECB book, but everything these days is modeled. So I would have to model it with vermiculite. And I think I did that just for like a sort of a, you know, clear section, and that you gain, you know, another, call it R3 effective. So you can basically shave off maybe an inch of insulation. So maybe you did it down to 20, or from 19 down to 18. But I think that's where, you know, using a 3-inch brick helps, because, you know, it's 5/8 of an inch you're saving, you know, using a 1-inch cavity instead of 1.5-inch cavity, because you're saving a 1/2 inch. They start to aggregate into and get you into a smaller cross section, right? So I think those kind of tricks can help us, but we are lacking the thermal data. And then more importantly than just having the thermal data is getting it into the designer's hands. Because right now they will basically use, like I reached out to some friends at Intuitive and just said, well, what are you guys doing? And they said, yeah, we still use this BC Hydro spreadsheet. We made a more user-friendly version, which I totally understand because it's not the most user-friendly, but we still use that. And then we try and find the detail in the thermal catalog. And if there's budget, so there has to be budget, and the detail is missing that we want, we will model it, but they kind of have to have budget to do that, right? Because it takes time. So, you know, I think that was sort of reasons that we sort of as an industry have to have a sort of a comprehensive thermal catalog, wood, steel stud, etc. And so these put that in the hands of designers. And I think, you know, even giving them maybe like a technical aid on the trade-off system, because I've seen actually a personal experience, had a warehouse down in Medicine Hat that originally had 6 inches of Roxol on it, and we went down to 3. So just by properly thermal modeling it, right? So yeah, that's a big difference in the depth of the wall.
Yeah. So lots of questions still to be answered.
Yeah.
Well, thank you, Mark. I think we're getting close to 3 o'clock here, so we can certainly wrap. Is there any other questions for Mark before we wrap up? Okay. Well, with that, I wanted to thank everyone today. I think at this point I just would like to see what we think now. That we'll loop back around if we can answer these questions after everything that we've been through today. Give you a minute or two. All right, well, that looks a little bit better than this morning. So we're 100% on, is masonry a green building material? And then here we go with, is the masonry industry well positioned to participate in the transition to the green economy? So 91% yes on that one, and a couple not sure. So I think out of this today, I think we can certainly see that the work is cut out before us. But I believe that we have the right people within the industry to start addressing these challenges moving forward. It's certainly something that's not going to go away anytime soon. And if we want to continue being the premier building material, and that's going to build beautiful communities across North America. This is certainly something that we need to address. So we're hoping to continue this conversation, and if anyone on today has any questions or suggestions or thoughts about what the industry can do, or questions about what you saw today, please feel free to reach out to myself or any of the panelists here. We will be making these presentations available for everyone on our YouTube page, and we'll be getting that out. So thanks again, and another quick thank you to our sponsors that certainly helped make this possible. Our platinum sponsor, Brampton Brick, and our silver sponsors, Ariscraft, Permacon, and the Alberta Masonry Council. Thank you, everyone, and enjoy the rest of your day.